topics which you need to focus. The first one is water quality. So all concepts in water quality, right, are water quality parameters. You have to go through them with the numericals. Especially you need to focus on hardness, right, alkalinity, pH, then problems. I'm talking about numerical problems. You'll get here only. Then in addition to that, E. coli test. Okay. Remaining things also important, DO, etc. So if you have better idea of all water quality parameters are important, but problems you can expect here, numericals. Okay. Then second important topic is sedimentation concepts. Sedimentation tanks and design concepts. 100% will get one question from here. One question guarantee, because we talk about this subject, right? 4 times we talk about the sedimentation. Therefore, very, very important, numericals and all. Then third, sedimentation aided with coagulation. Here you need to focus on numericals. Numericals related to alum dose, alum requirement. Okay. Then design of rapid mixing unit, flocculator, etc. Okay. Next, you need to focus on filtration numericals. Filtration and design of filters. Design of slow sand and rapid sand filters. If you have thorough idea regarding them and numericals, then you can score. And fifth one is disinfection and numericals on chlorination. So it's supposed to be very clear. Chemistry related numericals are very, very important. In addition to that, Hardy cross method basics. Basics. And seventh, population forecasting methods. Population forecasting methods. Okay. These 7 topics you are thorough. From the above 7 topics, we will get 3 to 4 questions will get. Okay. Be thorough with them. Then coming to wastewater engineering. Water supply engineering. This is water supply. Okay. Here, few topics: estimation of dry weather flow, wet weather flow. Sewer design concepts. Problems on BOD. Numericals, especially. Numerical questions. Then fourth, design of grid chamber. If at all any question they ask, this is the grid chamber only. Then activated sludge process ASP numericals and trickling filter numericals. Next, sludge treatment. Here also numericals. Septic tank and oxidation pond. Numericals. Disposal of effluents. Numericals on mix formula. Right? Then ninth, solid waste management numericals. These are additional topics. Then the air pollution and control. Numericals on conversion from ppm to microgram per meter cube and microgram per meter cube to ppm or ppb. Okay. Second, numericals on meteorology, especially lapse rates. Okay. And third, numericals on control equipment. Especially electrostatic precipitator and fabric filters. That's all. These 10 topics you are thorough, you will get 3 to 4 questions. Okay. So you are thorough with these 10 topics and this 8 topics, 7 topics in water supply, 100% you get score. Okay. So let us fast quickly. Let us brush up once again. Revise the contents, what we have studied in our course in brief. Okay. So I'll try to cover maximum so that I asked you to prepare notes on your own. Those who have prepared your notes on your own, you just go through that and verify with my, with our revision. Mostly it is whatever we covered in the class, that only we revise once again. So let us start with the first topic. Population forecasting methods. Here what you need to remember is only those formulae. Okay. Arithmetic increase method, geometric increase method, incremental increase method, what formula we use, what and how to find out those statistical information, statistical constants, statistical variables, how to work out them. If you work out them, then using the formula, by substituting in the formula, we can work out the future population. So arithmetic increase. In arithmetic increase method, what we do? Future population we work out by using formula Pn is equal to P naught plus N into X bar. How to find out this X bar? That's all. It is X1 plus X2 plus Xm by M. Same values are there. What is X value? How to find out X value? X value is nothing but difference in population between two successive time periods, Pi plus 1 minus Pi. So we'll prepare a table here. So here time will be given, population will be given, then X values will be given. So from this you can calculate X bar. Using these X values, you can find out X bar. So you can simply write this as sigma xi by m, like this. So P naught is latest population. In this, P naught is among all population data, latest known population is taken as P naught. Then Pn is future population. Future population at time Tn. So this is how we work out, right? Now to find out n value, this n value is nothing but Tn minus T naught by 10. So suppose x value calculated per decade, n value worked out in decades. If x bar calculated per year, we work out n value also in years. So this depend on the past population data, how they give past information. Past data is given statistical information. Past statistical information is given. Every year population data is given, x bar we calculate per year, right? Every decade population is given, x bar we calculate in terms of decades, right? So based on that, we'll work out. Tn minus T naught you take, you will get number of years. So T naught is population, latest known population at time T naught. That is population at time T naught. That's all. Usually we apply arithmetic increase method for old and settled communities. How can you say that say communities evolved? Suppose choice is given to you, then using this we can find out. So almost DP values we calculate. If DP values are very close, then we apply arithmetic increase method. So DP1 is almost same as DP2. DP2 is almost same as DP3. Almost close. What is DP? This is nothing but DP only. Change in population between two successive time periods. This is nothing but DP, XI only. So these XI values are very close. Then we work out arithmetic increase method problem. Suppose choice is left to you. Then coming to geometric increase method. Again, formula you have to remember. So Pn is equal to this P naught into e power R into Tn minus T naught. Suppose R value is given. If R value not given, we work out by statistical equation. 1 plus R bar by 100 whole power n. So if R is given, R is nothing but change in percentage change in population. Percentage, geometric average of percentage increases. This is geometric average of R or R bar, whatever it may be. Geometric average of percentage increases. Percentage increases of what? Population only. So R at any time you can calculate by using change in population by original population into 100. Change in population, Pi plus 1 minus Pi by Pi into 100. So if you use this equation, you will get change in population between two successive time periods, Ti plus 1 and Ti, right? Then R values will get R1, R2. Then we'll work out R bar. This R bar is equal to R1 into R2 into dot 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 Rm whole power 1 by m. So this is how we work out R bar. Okay. If R is given, is well and good. No need to use statistical equation. Straight away we can substitute here. Remaining things are same. N and all carry same meaning. N is nothing but Tn minus T naught. Sometimes it is worked out in decades. Sometimes it is worked out in years. Depending upon R. R calculated per year. N also we substitute in years. R calculated per decade. N also we substitute in decade. Okay. Similarly, incremental increase method. Incremental increase method. In incremental increase method, how we work out? Same formula, P naught plus N into X bar plus N into N plus 1 by 2 into plus or minus Y bar. So this X bar and Y bar, how to calculate? Right here, this method normally we used for rapidly growing communities. How you can know that community is growing rapidly? DP1 is less than DP2, DP2 is less than DP3. Such type of communities are fast developing communities. Such communities we apply geometry. Suppose confused trend is there, DP1 is greater than DP2, or DP2 is less than DP3. Suppose choice is left to you, or DP1 is less than DP2, DP2 is more than DP3, then also you can apply incremental increase method. X bar, only Y bar you need to work out in this method. So that Y bar is equal to, so Y1 plus y2 dot 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 ym by m. How to find out these y values? Y values are worked out by comparing x values. So xi plus 1 minus xi will give y values. That's all. So only equations you have to remember. Then decreasing growth rate method. Usually, so dp1 is greater than dp2. This kind of trend it shows we apply decreasing growth rate method. So choice is not given to you. Then you have to observe the trend and decide which method best fit for that population data. If choice is, if you only mention solve problem by arithmetic method, solve problem by geometric method, solve problem by incremental method or something like that, then straight away formula substitution. Choice is left to you. Only population data is given, right? You have been asked to choose a method and work out. Then this we observe DP values. Then based on that we get idea which method of is more appropriate to work out future population. Then we work out future population by using appropriate method. Okay, that point you have to remember. So population at any time is equal to the P naught into 1 plus R naught minus D bar by 100 into 1 plus R naught minus 2D bar by 100 and so on 1 plus R naught minus ND bar by 100. So using this formula we can work out. Here how to work out D bar. D bars are nothing but decrease in average decrease in percentage increases. Average decrease in percentage increases. This is known as D bar. So how to find out D bar? Based on D values. So D1 plus D2 dot 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 dm by m. How to get D values? Di is equal to compare R values. Ri minus Ri plus 1. So decreasing in percentage increase. So percentage increases we work out R values. So compare them Ri minus Ri plus 1 you take, you will get D values. So then take D bar and substitute in the formula. So this is how you have to remember. But they are not asking nowadays questions on population forecasting, but numericals you can't ignore in GATE exam. Any numerical is there, any scope and chance is there for numerical, by default you're supposed to be ready to solve that problem. You're supposed to know the concept. You're supposed to know the how to work out the problem. Okay, so let us not take chances. Then coming to sources of water, this and all not required. In conveyance, one question is possible. Conveyance of water, that is to take water from source so and so point from source to so and so place. Then what is the size of the pipe required and what is head loss? This kind of things they may ask. Of course, it is partially related to fluid mechanics, partially to W. So like this. So this is a source from which they are drawing water and they are supplying here into reservoir here. So in this case, what we do is, so that is the elevation difference between source and supply is h meters. The distance between source and supply is L meters. Right? Therefore, what we do is, we equate this to this HF is equal to H we take, which is equal to FLV square by 2CD, or you can take FLQ square by 12.1 D power 5. So from this, you can find out diameter of the pipe or whatever you require. So based on that, they are asking questions. And last 10 years, a couple of times, 2 times, this question they asked in GATE exam. Of course, this is related to fluid mechanics and as well as W. Okay, either they may ask for a given situation like this, they may ask you find the diameter, or for a given diameter pipe carrying water from source to supply, what is the head loss in a pipe? If they ask head loss, then it is a fluid mechanics problem. If they ask diameter of the pipe, it is W problem. So W means we design. So this is called diameter of the pipe. So they have been asked, you have been asked to find out diameter of the pipe. Diameter of the pipe or capacity of pump. But pumps and all removed no syllabus. Now hydraulic machines are not there. Therefore, pump concept you can ignore. So this pipe concept you have to remember. That's all. Then very, very important topic is water quality. Water quality, what you need to remember is based on size of impurities. Impurities are classified into 3 categories. Suspended impurities, their sizes they are important. Okay, those sizes you have to remember. Remaining not required. Suspended impurities, colloidal impurities, and dissolved impurities. 10 power minus 1 mm to 10 power minus 3 mm. The sizes you have to remember are 100 micron to 1 micron. They are called suspended. 1 micron means 10 power minus 6 meters or 10 power minus 3 mm. Okay. Similarly, colloidal impurities. It is 10 power minus 3 mm to 10 power minus 6 mm. Their sizes 1 micron to 10 power minus 3 microns. They are called colloidal. Similarly, dissolved impurities. These sizes are important. Specifications. 10 power minus 6 mm to 10 power minus 8 mm or 10 power minus 3 micron to 10 power minus 5 micron. They are called dissolved impurities. And coming to water quality, first one is physical water quality. In physical water quality, you have to remember all those things. How temperature is measured, how turbidity is measured, how color is measured, how odor is measured, right? So what are the parameters? First, temperature, right? Drinking water standard is water quality standard. How much it is? 10 degrees Celsius to 20 degrees Celsius. That's all. That much you have idea, more than sufficient. Remaining things are not required. I don't think so. Color measured by tintometer. Measured on Burgess scale or Cobalt scale. Expressed in temperature measured by thermometer. Everybody knows that. So that's why I did not write there. Expressed in terms of true color units. TCU stands for true color units. And drinking water standard. The standards you have to remember. Should be 5 to 20 color units. Okay. That much idea is there, more than sufficient. Then turbidity. Nowadays, turbidity is measured by nephelometer. That nephelometer principle also important. Earlier, we used to measure by amount of light scattered. To measure turbidity, it measure amount of light scattered. Right angles to incident light. So 90 degrees scattering. It measure 90 degrees scattering to work out turbidity. Nephelometer. Expressed in NTU. Nephelometric turbidity unit, or sometimes expressed in JTU. Nephelometric turbidity units. Nephelometric turbidity units, or sometimes JTU, Jackson turbidity units. Usually by nephelometric Jackson turbidity units normally used for outdated devices like Baylis meter, Hillier meter, like Jackson meter, like that we express in JTU. Both of them almost same. So turbidity, drinking water standards. Turbidity should be 5 to 10 turbidity units. Turbidity units. It could be JTU or NTU, no matter. Okay, that you have to remember. Then color. Sorry, color already discussed. No? Odor and taste. Odor and taste measured by? Odor is measured by? Osmoscope. Expressed in terms of TON. TON means stands for what? Threshold odor number. Threshold odor number. Okay. I forgot in here turbidity. Turbidity measured on silica scale. Turbidity measured on silica scale. Okay. That's also important. So threshold odor number is a dilution ratio at which odor is just detectable. So A plus B by A, where A is equal to volume of water sample in ml, water sample to be tested in ml. B is equal to volume of distilled water used in dilution. In ml. So A plus B is nothing but capacity of osmoscope is always constant. Osmoscope is some kind of inhaler kind of thing. So you have to keep water sample inside the osmoscope. So its capacity is 200 ml. So A plus B is always 200 ml. 200 by A also you can write, or otherwise you can write straight away 200 by A. That way also you can calculate. Okay. Suppose A is given, B is not given, then B is equal to 200 minus A. If you take, you will get B. Like that way also you can work out sometimes. So these are the 4 physical water quality parameters. Okay. Next, coming to chemical water quality, the very important parameter is pH. I'm writing only important topics. I'm discussing here only important things. Okay. Just 1 minute. Let me drink water. In chemical water quality, so you can expect questions on pH. pH is equal to before that numericals also possible from solids. Solids are measured by gravimetry. Among all those things, important is TDS. TDS is equal to final weight minus initial weight by volume of sample filtered. So final weight of crucible. Final weight of crucible after oven drying. WI is equal to initial weight of empty dry crucible. V is equal to volume of filtered water sample tested. Filtered water sample is free from suspended and colloidal particles, therefore suspended particles, therefore only thing present is colloidal dissolved solids. So colloidal dissolved solids together known as TDS. Volume of filtered water sample tested. Okay. So TDS includes both colloidal particles plus dissolved particles. So TDS quickly we can measure by measuring electrical conductivity of water. So K into electrical conductivity, where K is a conductivity meter constant. Conductivity meter constant. And it will give you that value. And EC is electrical conductivity of water. Electrical conductivity, if you measure, you can also measure approximately TDS. Water in micro mos. OHM, MOH. Then straight away will get TDS in milligram per liter. Straight away. Okay. That way also you can measure quickly. But correct method is this one. This is exact method and this is approximate method. Testing is always perfect. This is approximate method. Approximately you can measure. Approximately we can estimate TDS like this by measuring electrical conductivity. Approximately. Okay. On TDS only important, rest of them I don't think so. Then coming to pH, all numericals are important based on formula H plus into OH minus is always constant. This value is always constant, 10 power minus 14 moles per liter. Okay. This is one formula. Other formula is pH plus POH is equal to 14, where pH is equal to log 10 1 by H plus ions, where POH is equal to log 10 1 by OH minus ions. So this is how we can. So based on this, questions they will ask. You may ask H plus ions and find POH. You may ask OH minus ions and find pH of water, like that. Vice versa, they'll ask questions. You are thorough with how to solve these questions. So pH value straight away cannot include in calculation. Calculation part always we keep H plus ion concentration. H plus ions we take and work out. The product of H plus and OH is always constant. Should lie anywhere between 10 power. I forgotten TDS in drinking water standard. Drinking water standard TDS should be less than or equal to 500 milligram per liter. Drinking water standards are important. That's only theory that you can expect. Okay. And pH, I can also measure pH by using pH meter directly, straight away. pH is measured by potentiometer. In our language, we call it as pH meter. It's a digital electronic device. Straight away you can measure pH. So drinking water standard. Standard for drinking water is pH should be anywhere between 6.5 to 8. 8 it is okay. Above 8 it is not allowed. Less than 6.1. pH is not dangerous. It only cause minor problems. At greater pH is less than 6.5, corrosion problem, right? pH is more than 8, scaling problem. So therefore it should not be more, it should not be high. Scaling problem. Corrosion problem, scaling problem. Because of this, you're supposed to keep pH value anywhere between 6.5 to 8. Drinking water point of view, there is no much significance, right? But property point of view, yes, pH is objectionable. Drinking purpose, water having any pH, you can comfortably drink. That's all. That much idea is there more than sufficient related to pH. Next. Next one is acidity, alkalinity. Numericals are important. Acidity is not so important. Here, what numericals is total alkalinity. How to find total alkalinity? Ta. Okay. It is carbonates into 50 by 30 plus bicarbonates into 50 by 61 plus you want to work out, you can add here OH minus ion concentration into 50 by 70. Usually pH greater than 10.2, carbonates and bicarbonates not contribute alkalinity. So it's only pH, that is OH minus ions. So total alkalinity caused by OH. OH minus ions is more than carbonates and bicarbonates. Therefore, they are neglected. Okay. when pH between 4.2 to 10.2 in this range, total alkalinity caused by carbonates and bicarbonates is more. Carbonates and bicarbonates is more compared to total alkalinity caused by OH, compared to OH minus ions. Therefore, in this pH range, OH is neglected. Therefore, OH minus ions neglected in this pH range. So, all three do not contribute alkalinity. When OH contributing alkalinity, you can write like this: OH into 50 by 17. When in the pH range greater than 10.2. So, total alkalinity is equal to carbonates into 50 by 30 plus bicarbonates into 50 by 61. This you can write in the pH range 4.2 to 10.2. That's how we can work out to total alkalinity. Okay? Total alkalinity we can also find out by titrometry. So the titrometric procedures, all titrants and indicators are important. So total alkalinity can also be measured by titrometry without finding those substances. So titrant used to find out alkalinity is acid, H2SO4, and indicators. Titrants and indicators are important. Indicator is, what is indicator? Two indicators we use. One is phenolphthalein and methyl orange. Phenolphthalein will give P alkalinity, methyl orange will give M alkalinity or T alkalinity. Okay, that's how. So we also have drinking water standards. Alkalinity in drinking water should be, drinking water standard is there for alkalinity. Alkalinity in drinking water should be preferably less than or equal to 200 milligram per liter. If it is more than 200, it causes bitter taste. Alkalinity cause bitter taste. Alkalinity cause scaling problem. Then scaling is one problem. Second problem is incrustation, water form. Material lose its strength. That one is bitter taste. So because of these reasons, we have to work out alkalinity in water. Acidity you can neglect, but alkalinity you have to find out. Okay. Next parameter, hardness. This is also a very, very important parameter for GATE exam point of view. So total hardness is equal to call it as TH. So this TH is equal to, we express hardness, alkalinity and acidity in terms of milligram per liter as CaCO3. Alkalinity also expressed in milligram per liter as CaCO3. So all these three parameters express the same unit system. So it is calcium into 50 by 20 plus magnesium into 50 by 12. So this is how we can find out total hardness. So total hardness is caused by calcium and magnesium, iron, strontium, manganese. They do contribute, but their contribution is very small. Okay, that's why they are neglected. Calcium and magnesium is the main. So this calcium, magnesium react with the carbonates, bicarbonates, chlorides, and sulfates. Okay, so calcium carbonate, calcium bicarbonate, calcium chloride, calcium sulfate. Calcium carbonate, calcium bicarbonate cause temporary hardness. Calcium chloride, calcium sulfates cause permanent hardness. Similarly, magnesium carbonate, magnesium bicarbonate cause temporary hardness. Magnesium chloride, magnesium sulfate cause permanent hardness. Okay, there are two types of hardness. One is temporary hardness, that in our language we write as carbonate hardness. Shortcut we write CH. In our language we call it as temporary hardness. Temporary hardness is caused by carbonates and bicarbonates. Permanent hardness is caused by chlorides and sulfates. Of course, calcium carbonate, calcium only. These cations react with these anions and produce. Second one is non-carbonate hardness. We write it as NCH or permanent hardness. Okay. So total hardness we can also work out by sum of carbonaceous hardness plus non-carbonaceous hardness. This way also you can find out total hardness. Otherwise, calcium and magnesium concentrations, if you know, you can find out total hardness. Okay. So how to find out this carbonaceous hardness and non-carbonaceous hardness in water? One minute, my system problem. There's a problem. There's a problem with the board. I don't know what it is. Let me talk to these guys. బోర్డు రాయడం లేదు, ఇది బంద్ అయిపోయింది. చూడు రమ్మని అబ్బాయిని. Yes, Ranjit, what is your question? Yeah, you have doubts, you can ask me. No problem. My board is not working, so I asked him to correct it. Okay, please kindly cooperate. Technical issues are there here. Oh, just breakfast just now. Ide undu. Right. So total hardness is equal to carbonaceous hardness and non-carbonaceous hardness. Okay. How to work out this carbonaceous and non-carbonaceous hardness? So we work out this carbonaceous and non-carbonaceous hardness by establishing relation between total hardness and total alkalinity. So total hardness is greater than total alkalinity, then carbonaceous hardness is equal to total alkalinity. Non-carbonaceous hardness is equal to total hardness minus carbonaceous hardness. So total hardness is less than or equal to total alkalinity. Then carbonaceous hardness is equal to total hardness, and non-carbonaceous hardness is equal to 0. Based on these relations, in last 20 years, almost 18 times questions came. 18 questions. 18 years they keep on asking same question in last 20 years. But still students, they go wrong. So these two you have to remember. Okay. These relations are very, very important. Carbonaceous hardness is equal to when total hardness is greater than total alkalinity, carbonaceous hardness is equal to total alkalinity. Non-carbonaceous hardness is equal to total hardness minus carbonaceous hardness. Total hardness is less than or equal to total alkalinity, then carbonaceous hardness is equal to total hardness and non-carbonaceous hardness is equal to 0. So these relations are very, very important. Okay. Remember. That's all. You can expect questions from this. Our total hardness you can find out by using calcium into 50 by 20 plus magnesium into 50 by 12. Or otherwise, sometimes milli equivalents per liter if they give, straight away you can write total hardness is equal to calcium into 50 by 20 plus magnesium into 50 by 12. Provided that calcium concentration, magnesium concentration is given in milligram per liter. Suppose calcium and magnesium is given in milli equivalents per liter, straight away multiply with 50. Calcium and magnesium concentrations are given in milli equivalents per liter, straight away you can multiply with 50. Okay. Similarly, total hardness also. Total alkalinity. Total alkalinity is equal to usually carbonates and bicarbonates. Carbonates into 50 by 30 or bicarbonates into 50 by 61. When concentrations are given milligram per liter, you can use this. Or milli equivalents per liter is given carbonates into 50 plus bicarbonates into 50. So straight away you can work out if they are given in milli equivalents per liter concentrations. Okay. So we can work out total hardness, total alkalinity in milligram per liter as CaCO3. So straight will get milligram per liter as CaCO3. This also will get milligram per liter as CaCO3. Then you can find out carbonaceous, what amount of carbonaceous hardness present, what amount of non-carbonaceous present based on this comparison between total hardness and total alkalinity. Okay. So this is important. The rest of them are light. Next, coming to dissolved oxygen questions, they may not ask, but theory questions. Drinking water standards they will ask. So drinking water standard with respect to hardness is, so it should be less than 300. Preferably total hardness should be less than milligram per liter as CaSO3. So hardness cause problems to property. Drinking point of view, good. Hardness cause, right? Corrosion problem, scaling problem, bitter taste, and increased soap consumption. Increased soap consumption causes economic loss. Other than that, there is no health point of view, no problem at all. Health point of view, hard water is good water. Property point of view, objectionable. That's why we remove hardness from water. Coming to remaining parameters, chlorides measured by Morse method. Titrant used for chlorides estimation is silver nitrate. Indicator is potassium chromate. For hardness also measured by titrometry. I forgotten. Titrometry means two things you have to remember. One is titrant, the other one is indicator. Titrant is EDTA, ethylene diamine tetraacetic acid, and indicator is erythrome black tea. So all these titrants and indicators you have to remember. There is another option. Erythrome black tea. Titrants and indicators for every parameter important. This method is called, right, Versenate method or EDTA method. People call it as Versenate method or EDTA method. Hardness is measured by Versenate method or EDTA method. Chlorides are measured by Morse method. It is also titrometry. Titrant is silver nitrate. Indicator is potassium chromate. Similarly, dissolved oxygen. Shortcut we write it as DO. DO is measured by Winklet's method. This is also titrometry. So titrant used is sodium thiosulfate. Sodium thiosulfate. Indicator is starch. Starch is used as indicator. Okay. Chlorides drinking water standard, it should be 250 milligram per liter. Chlorides. Okay, remember. Dissolved oxygen drinking water standard should be 3 to 4 milligram per liter. So very important parameter. So dissolved oxygen sufficient amounts are not there. Water smell bad and taste bad. So smell and taste also important now. So therefore, dissolved oxygen you have to maintain in water. It's an important parameter for exam point of view also. Similarly, chlorides, sulfates measured by turbidimetry. Using barium. So barium is added to water that produce barium sulfate. React with sulfates in water, produce barium sulfate. That barium sulfate is turbid solution. So based on turbidity that appear in water, we measure sulfates in water. So sulfates cause what problem? Sulfates cause, excess sulfates cause what problem? What problem? Sulfates cause laxative problem. Laxative problem. Loose motions. Laxativeness means loose motions. Loose motion sometimes leads to death also. For standard, drinking water standard is sulfate should be less than 250 milligram per liter. Okay. Next, fluorides. Fluorides more than 1 milligram per liter, less than 1 milligram per liter cause dental caries problem. Dental caries or dental cavities. Fluorides more than 1.5 milligram per liter cause fluorosis. This is known as fluorosis. So this fluorosis, dental fluorosis and skeletal fluorosis. Skeletal or bone fluorosis it causes. So therefore, drinking water standard with respect to fluorides is it should not be less than 1, it should not be more than 1.5. It should be preferably 1 to 1.5 milligram per liter. Fluorides must be anywhere between 1 to 1.5 milligram per liter in water. Should not be less than 1, should not be more than 1.5. Next, nitrates. If present more than 45 milligram per liter, it causes a disease known as blue baby disease. Blue baby disease means technically it is known as methemoglobinemia. So that's why it's nitrates standard is nitrates preferably less than 45 milligram per liter. Okay. Then iron and manganese cause color. So standard is iron should be less than 0.3 milligram per liter. And manganese should be less than 0.05 milligram per liter. These are the standards for both iron and manganese. Okay. So in addition to that, toxic substances, usually heavy metals. Which eventually leads to death only. What are the toxic substances? Lead, arsenic, barium, boron, cadmium, chromium. So such type of things. Okay. Phenols, mercury, cyanide. These kind of things are called toxic. Etc. You can write any number of things. So they cause death only. So therefore, we need to be careful about them. So next, biological water quality. So E. coli test. In E. coli test, what we do is, right, E. coli organisms ferment lactose and produce gas. That is the basis. E. coli are non-pathogens. Pathogens are disease-causing organisms. Ferment lactose and produce gas. So E. coli organisms are known as indicator organisms. E. coli present means pathogens present. It indicates presence or absence of pathogens. Pathogens are disease-causing organisms. E. coli absent means pathogens absent. That's why they are called indicator organisms. Okay. So E. coli test results are expressed in MPNR, E. coli index. MPN is bacterial density, which is most likely to be present in given test results. Which is most likely to be present. Are given test results. MPN means most probable number. Density, which represent density of microorganisms. So drinking water standard is one number in 100 ml is present, you can accept. Anything more than one number is not acceptable. We can reject the water. So density of organisms, number of organisms present in 100 ml of water sample. Okay. E. coli present means pathogens present. E. coli absent means pathogens absent. That's all. That's why E. coli organisms are called indicator organisms. So this much idea is there more than sufficient. Numericals on E. coli, numericals on MPN. They're also important for exam. Just go through the class notebook, then you'll get idea. Okay. Next topic is sedimentation. Sedimentation is very, very important for GATE exam point of view. Not only GATE and every competitive exam, sedimentation is very, very important for civil engineers. In sedimentation, what we do is we capture particles by gravity. Capturing any particle from water by gravity is called sedimentation. Capturing any particle by gravity. Gravity means sulfate. Inertial force by gravity is known as sedimentation. Here numericals are very, very important. We have 4 types of sediments: discrete sediment, discrete particle sediment, flocculent particle sediment, hindered settling, and zone settling or compression settling, like this. So 2 we come across with water treatment, water supply, and 2 we come across with in wastewater engineering. Okay, but all concepts are same. First possible question in sedimentation is settling velocity. How to calculate settling velocity of particles. settling velocity of particle, any particle, is equal to, it is estimated by Stokes equation. Stokes equation, if we simplify, you will get equations which are very, very simple. This is called Stokes equation. The Stokes equation you can simplify for laminar flow condition. In sedimentation tanks, laminar flow condition prevail. Therefore, for laminar flow condition, if we simplify sedimentation tank, laminar flow prevail. And you can simplify those equations for laminar flow. G into S minus 1 d square by 18 mu. Or sorry, this is nu, kinematic viscosity. This is mu. This we also can find out. This mu is known as kinematic viscosity. It should be substituted in meter square per second. Dynamic viscosity. Dynamic viscosity. Kinematic viscosity and dynamic viscosity. Okay. So these are laminar flow conditions. You can use these equations and you can work out. Or you can use Hazen's formula also. When temperature is given, you can use Hazen's formula. Straight away this will give settling velocity in mm per second. Okay. This equation only gives settling velocity in mm per second. Normally we don't use this much. So I'm removing this. These two only important basic equations. Of course, which are derived from Stokes equation only. From this equation we got those. Okay. This is the one formula which is supposed to be thorough. And few design concepts. The first one is surface loading rate or surface overflow rate, which is called SLR and SOR. Only revision now this is. Surface overflow rate, we denote it by V naught, which is equal to Q by surface area of sedimentation tank. Or plan area of sedimentation tank. So surface area is known to you, you can find out V naught. Or V naught is known to you, you can find out surface area. So like that questions you will frame. So you can answer. That is second one. Third one is detention time. So detention time is equal to average theoretical time taken by the water to travel inlet to outlet, which is nothing but V by Q. So for rectangular tanks, rectangular sedimentation tanks, surface area is equal to L into B, V is equal to L into B into H. So everything you will get. For circular tanks, A is equal to pi by 4 d square, V is equal to surface area into depth. Okay, that's how we can find out for circular tanks and rectangular tanks. Two types of tanks we have. That's it. And in addition to that, efficiency, particle removal efficiency. Which is ratio between settling velocity of that particle to surface loading rate for which sedimentation tank is designed. Vs by V naught into 100. Okay, that's called efficiency formula. Efficiency of particles. Overall particle removal efficiency. Overall particles removed is equal to, there are so many particles present in water, so it is sigma pi into efficiency I by 100. This is efficiency of ith particle only. Then settling velocity of ith particle we take and we work out. That's how we can find out. And particle removal efficiency can also work out by concentration of particles. By knowing concentration of particles also, you can find out particle removal efficiency. Ith particle removal efficiency of ith particle is equal to, it is settling velocity of ith particle by V naught into 100, no doubt, which can also work out by C in minus C out by C in into 100. This we also can find out of ith particle. There are many particles present in water. Each particle has got its own settling velocity. Okay. Concentration in, concentration out. So it is a sedimentation tank. You apply water from one end, you collect water from other end. Here concentration is C in, concentration out is C out. Concentration removed is how much? That removed particle accumulated at bottom as a sludge. Here concentration is equal to C in minus C out. The difference between C in and C out will accumulate at bottom of the sedimentation tank as a sludge. So overall removal efficiency can also work out by overall efficiency. Overall particle removal efficiency. All you can write here. This also you can write, and which is also equal to sigma of C in minus C out of ith particle into 100. That way also you can find out. Overall removal efficiency. All these formula you are thorough. Any question you can answer related to sedimentation tanks. Okay. Let us have a small break. Let me have a cup of tea. I'm getting sleep. Let me have a cup of tea. I'll come back. Okay. Just 10 minutes break. Yeah. Shall I start again? Yeah, Thomas equation also you can use for finding MPN value, but very rare. Straight away we can use tables, MPN tables we can use and work out MPN value. Okay. Usually tables we use, ready-made tables are there, MPN tables. Using them we work out. Anyway, let us see. Next, coagulation. Here, two types of questions are important. One is working out chemical requirements. All I'm required. So, alkalinity required. Coagulating water with alum. Usually, alum is very popular. So, alum requirement, alum and alkalinity requirement. From there, one question you can expect. Okay. So, we can find out by alkalinity required in water. It is 3 into 100 by 666 into alum dose. So from this you can find out alkalinity required. Sometimes alkalinity deficiency is there, right? Then to fulfill that deficiency, we add quicklime. Alkalinity deficiency in water. So alkalinity present minus alkalinity required minus alkalinity present. Alkalinity present in water, already present in water. So to fulfill alkalinity deficiency, sometimes we add quicklime. So dose of quicklime required is equal to it is 56 by 100 into alkalinity deficiency. So like this we can work out. Then total alum required per day is equal to required per day per month they'll ask. So Q into alum dose multiply, then you'll get this one. This you multiply in mld, this in milligram per liter, straight will get total alkalinity, total alum required per day. If we get per day, per month, per year also can work out. Total alum required per month. Required per month means total alum required per day into 30. Required per day into 30. Total alum required per year means not only alum, any chemical requirements we calculate in the same fashion. Q multiplied by the requirements. Q total alum required per day into 365. So you will get kilograms, you can convert into tons also. That's how we can work out problems. 365. Similarly, total lime required per day, total lime required per month, total lime required. Instead of alum, we'll take a dose of lime. If you multiply dose of lime required per day, lime required per month, something like that. Okay. That is one time kind of question. Not only that, any kind of chemical requirement we work out by multiplying Q with any chemical requirement, total amount of any chemical, total amount of any substance, required per day is equal to Q into concentration of substance, or otherwise Q into dose of that substance. So substitute Q in mld, concentration milligram per liter, or substitute Q in mld, dose in milligram per liter. This product will give so and so kilogram per day. Then once you get kilogram per day, then you can, by multiplying with 30, you will get per month. If you multiply with 365, you will get per year. So that is how we can work out the things. This kind of questions they are frequently asking in GATE exam, IAS exam, etc. 1 mark, 2 marks questions. Okay. In addition to that, what else is important is rapid mixing unit. Rapid mixing unit design is based on 2 parameters, right? So rapid mixing unit power requirement or velocity gradient formula. Some questions they are asking on velocity gradient formula. G is equal to root of P by V mu, where V is equal to volume of rapid mixing unit. Volume of rapid mixing unit in meter cube. P is equal to power in watts. And mu is already we know, coefficient of dynamic viscosity. Okay. One question they're asking. And the detention time, using detention time, we can find out volume. So V is equal to Q into detention time. I forgotten to tell there in the sedimentation tank, there are some concepts are there in sedimentation tank. For 100% removal of particles, I forgotten, I supposed to write here. Okay, I'll write here. For 100% removal of any particle from sedimentation tank, conditions are one is settling velocity of particle should be greater or equal to V naught. Second one is, right, settling time of particle should be less than or equal to detention time of water, L by VH. So using these two also we can work out the things. Okay. So many problems we work out based on these relations. So detention time. Detention time is very, very important parameter. Detention time is equal to, it is volume by discharge. I wrote here, I think. Detention time is equal to volume by Q. So exactly same way. Anywhere detention time we can calculate using this. So what you can find out, volume of sedimentation tank also you can find out using detention time. Okay. Same way here also. So detention time is equal to volume by Q. Volume is equal to detention time into Q. Okay. This is one thing. Even flocculator also same way we work out problems. And sedimentation tank design you know already. Even flocculator also G value only changes. It is 20 to 80 second inverse we provide. For this one G value, rapid mixing unit G value is equal to, it is 700 to 1000 second inverse. Concepts are same. Here also same we can work out for flocculator. G value is equal to root of P by V mu only, where V is equal to volume of flocculator. Volume of flocculator, which you can find out by Q into detention time. So detention time we provide here is equal to 20 minutes to 40 minutes. Usually that and all given to you. Here detention time provided is equal to 1 to 3 minutes. Rapid mixing unit 1 to 3 minutes only. Here 20 to 40 minutes. So volume of flocculator is rectangular tank. This volume is equal to L into B into H. And the depth will be given to you. L is to, using L is to B ratio, you can find out length of flocculator and width of flocculator. Just go through the problems, then you will get. Sedimentation tank design already idea is there. So that is how you need to brush up the things fast. You can't go through every point here. So fast, quick revision. You have to carry out quick revision. So overall idea already 1 or 2 times thoroughly if you revise, then quick revision is very simple and easy. Just write highlights. If just by looking at them, you'll get complete picture of the concept. Complete concept that get into your, before your eyes, will get it. Okay. Next is filtration. In filtration, filter design problems they'll ask. Either rapid sand filter or slow sand filter. So total surface area filters we work out first. area of filter required. Either rapid sand or slow sand, doesn't matter. Filter required is equal to, it is Q by rate of filtration, right? So rate of filtration for slow sand filter is different, rapid sand filter is different. That's all. That's the only difference. It is 100 to 200 liters per. You, of course, it will give you all these values. You need not worry. For rapid sand filter, that working operation, that and all not required for gate exam. IS exam important. Concept theory also. Gate not required. So after getting this, method one is fix the number of filters n. Find size of each filter. How to find size of each filter? First of all, you have to find out area of each filter. Area of each filter, L into B is equal to total surface area by number of filters. Then using L is to B ratio, you can find out length of the filter and width of the filter. That is method one. Method two, exactly opposite. Fix the size of each filter. L and B, and find the number of filters. Number of filters in operation, N means. So this N is equal to total surface area by area of each filter. What is area of each filter? Because L and B is known, no? Area of each filter is equal to L into B. That's it. That is second method. After that, in addition to that, what extra expected in case of rapid sand filter? Slow sand filter, that's all. In case of rapid sand filter, what is extra expected is percentage of filtered water. Percentage filtered water required to backwash. Required to backwash filter. Equal to, it is rate of backwash into duration of backwash into area of each filter by rate of filtration into duration of filtration into 100. So that will give percentage filtered water used in backwash. Area of each filter is there, they cancel out. Numerator it is there, denominator it is there. Right? In addition to that, what else is there? Head loss during filtration. This is also expected. This we calculate by Karman and Kozny formula. FZV square by GD into 1 minus N by N cube. Okay. So in this, F is equal to friction factor, which is equal to 150 into 1 minus N by Reynolds number plus 1.75. That's how we work out. Okay. And Reynolds number RE is equal to rho VD by mu into pi, which is also equal to VD by nu into pi. So where pi is equal to shape factor. That also given in the question. Remaining things, V is equal to rate of filtration, Z is equal to thickness of sand bed. This and all known to you. N is equal to porosity of sand bed. N is equal to porosity of sand. Sand bed. Sand only used as a filter medium. That is one possible question. Then third possible question is head loss during backwash. While backwashing the filter also there is head loss. Z into 1 minus N into S minus 1, or it is ZE into 1 minus NE into S minus 1. Where ZE is equal to thickness of expanded bed. When you backwash the filter, bed get expanded. Expanded bed, and NE is equal to porosity of expanded bed. So during backwash, bed get expand like this. This is a normal thickness of sand bed. This is Z. So while applying backwash water, what happens is backwash water is applied from bottom. This is rate of backwash or velocity of backwash water. When you apply, what happens? This bed get expand. The thickness of that expanded bed is called ZE. This is called ZE, and porosity of expanded bed is NE. Normal bed porosity is N. Okay, porosity of expanded bed. That you substitute, then you will get also. Then ZE and Z relation we can brought out by using equation ZE by Z is equal to 1 minus N by 1 minus NE. So using this relation we can brought out, we can find out ZE or NE whatever required. And we can also work out rate of backwash. At what rate water is applied for backwash? ROV people call simply RVB, velocity of backwash water flow. So velocity of backwash water flow is equal to settling velocity of sand particle into porosity of expanded bed to the power 4.5, where Vs is equal to settling velocity of sand. Settling velocity of sand grain. The settling velocity we can find out by using Stokes law or by using laminar flow condition equation. Rho P minus rho W into d by CD rho W, or this is for any flow condition. For any flow condition you can use this, or any laminar flow condition prevail, settling velocity you can calculate by using G into S minus 1 d square by 18 nu. This is for laminar flow condition. This and all we discussed already in the class. Okay, you just go through them. You'll get idea. These are the possible problems in filters. In addition to that, sometimes that is not required for GATE exam. This much idea is there more than sufficient. Relation between JD, relation between, Iwasaki equation is there. Iwasaki and Isaki equation. Iwasaki and Isaki equation you can use. Based on that, sometimes questions may be asked. So it is dc by C is equal to minus lambda into dc by dz, change in concentration, minus lambda into C. So this equation simplify and work out, then you'll get a lambda, which is nothing but filter constant. So this lambda value is equal to 1 by Z into ln C naught by Ct is also equal to 1 by Z into ln 100 by 100 minus efficiency. So when you pass water through a filter bed, sand bed, this filter bed, thickness is Z meters. So when you pass water through it, apply water on the top, and we collect water from the bottom. So concentration of particles in water initially is C naught. By the time water particles come out of the filter media is Ct, almost it becomes 0. So like that you could do. Efficiency of particle removal is equal to, therefore particle removal efficiency, how to calculate? Particles removed in filter. Nothing but efficiency. It is C naught minus Ct by C naught into 100. Particles removed by particles applied into 100. So that way also you can find out. Like this, all these concepts are clear to you. You can answer any question from filters also. That is not a big deal. Okay. So like this, short notes you have to prepare before exam. So 2-3 times, if you remember all these formulae, then at the time of writing exam, by reading the question, if you write given data, then immediately that appropriate equation strike in your mind, then comfortably you can answer the questions. So remembering, recollecting and remembering and recollecting at right time in the exam, at the time of writing exam is very, very important. That required practice. Okay. Because I taught so many number of times, every time I teach you, it is a revision for me. Therefore, I revise so many number of times. Therefore, I remember them. I recollect whenever I am teaching to you again. So it is easy for me. So more number of times you practice, it is more easy for you. Especially equations, you have to remember. Okay. Next, coming to disinfection. Disinfection, especially chlorination is important. Disinfection by chlorination. Chlorination and then numericals from there are important for exam point of view. Okay. Let us see what kind of numericals that do we have. So when it comes to chlorination, right, first numerical is percentage HOCl. Percentage HOCl is equal to 1 by, it is 1 plus K by H plus into 100. Percentage HOCl in this. Or fraction HOCl means you can remove that because HOCl dissociate into H plus and OCl minus. Ionization equation if you write, you will get relation between HOCl and OCl. That ionization equation is product of products by product of reactants. H plus into OCl minus by HOCl is equal to K. This ionization equation. From this you can write as OCl minus by HOCl is equal to, it is K by H plus. So you can write like this. For this equation, this is right. Okay. That is one question. Concentration of HOCl in water. Concentration of HOCl in water is equal to, it is chlorine dose. When you add chlorine to water, chlorine dissociate and produce HOCl and OCl. Chlorine dose produced in water into this percentage HOCl that release in water. So that will give concentration of HOCl in water. Right? This HOCl more form in water. HOCl is more effective than OCl. Therefore, we wish to have more HOCl. HOCl formation strictly proportional to H plus. H plus is inversely proportional to pH. So therefore, at low pH, there is more HOCl. At high pH, there is more OCl. So therefore, chlorine dose into percent HOCl will give concentration of HOCl. So based on this, some questions they will ask. Based on this formula also. Okay. In addition to that, then chlorine demand question. One question is there, chlorine demand. So chlorine demand in water is equal to, it is chlorine dose added to water, right, plus chlorine dose minus residual chlorine. How much chlorine remained in water? How much added, how much remained? That is called chlorine demand. Residual chlorine in water. Or chlorine dose added, what amount of dose is supposed to add is, you have to meet chlorine demand, at the same time it has to produce some residual. Plus residual chlorine. That way you can work out. Right? This chlorine is added in the form of bleaching powder. Then bleaching powder dose required is equal to, bleaching powder contain 20 to 25% chlorine. So it is chlorine dose required by available chlorine in bleaching powder. Right? So bleaching powder contains 30 to 35% of chlorine. Therefore, we use bleaching powder. So from there, you can calculate bleaching powders. Then I will ask total bleaching powder required per day, per month, per year, something like that. So total bleaching powder required per day is equal to Q into bleaching powder dose. Total bleaching powder required per month, per year, that also very common. So once you get per day, multiply with 30, then you get per year, required per month. Sometimes total bleaching powder required per year, like this we'll ask. Then you can calculate per day you get, per month, per year you want to get, multiply with our number of days in a month, number of days in a year, then you'll get monthly requirement and yearly requirement also. Okay, that is one possible question. Next is, in addition to that, what else is required is, okay, kinetics of disinfection, kinetics of chlorination. So percentage removal of organisms, percentage destruction of organisms. It's called efficiency. It is N0 minus NT by N0 into 100, where N0 is equal to number of organisms initially present in water. NT is equal to number of organisms remain in water after adding chlorine or any disinfectant remained at a time t, that is at a time 0. At time 0 N0, time t NT. So number of organisms removed is N0 minus NT by N0 into 100 will give a percentage destruction. Sometimes log removal will ask. Percentage removal otherwise. Sometimes you'll ask log removal. In US and all, they work out everything on logarithmic scale. In that case, so it is log 10 N0 minus log 10 NT also you can use. Right? Similarly, this number of organisms remained at any time you can calculate by using equation N0 into e power minus KT. This equation is called Chick's law. So efficiency also you can find out with the help of Chick's law by substituting N0 value there is equal to 1 minus e power minus KT into 100. This also will give efficiency. In this equation, K is equal to disinfection rate constant. And T is equal to contact time or detention time, whatever it may be, or exposure time, whatever it may be. Something similar to detention time only. So using this contact time, this detention time, you can find out volume of disinfection unit. Volume of disinfection unit also you can find out. Q into detention time. So like this you can work out problems. Then in addition to that, so relation between contact time and chlorine dose. Chlorine dose C. So this relation you can brought out by using equation equal to constant, where N is equal to dilution factor. So C is chlorine dose, T is contact time. So this also very useful relation. From this also you can work out so many number of questions. These are the things which you're supposed to keep in your mind to answer questions in disinfection. One more thing is breakpoint chlorination. In breakpoint chlorination test, it is a test conducted. We get breakpoint. Is a test and we make results. After conducting the test, we plot results to obtain the breakpoint. So we take residual chlorine on y-axis and chlorine dose on x-axis. From this, you can find out what is the dose to be added, so that we get protection at the same time. So at one point, curve rises 45 degrees. The point from which curve rises 45 degrees is known as breakpoint. So this point is called breakpoint. Dose again is that is called breakpoint dose. So at break point, two residuals are there. One is combined residual, combined chlorine residual. What is this residual? Free chlorine residual. So we have to get both of them. So therefore, we need to work out what is the dose to be added to produce stable residual. So chlorine dose is added beyond break point such that it produces stable residual. Chlorine dose added beyond break point chlorine dose. Such that combined chlorine residuals and free chlorine residuals form in water. Okay, so therefore total chlorine residual is equal to combined chlorine residual plus free chlorine residual. Combined chlorine residual means chlorine residual in the form of chloramines. Chlorine residual in the form of chloramines is called chloramines, which is monochloramine, dichloramine, etc. Trichloramine, etc. Form in water. They are dangerous also sometimes. Of course, chloramines are not dangerous. Okay. And free chlorine residual means residual chlorine residual in the form of HCl and OCl. HCl means hypochlorous acid. OCl means hypochlorite ion. Hypochlorous acid. Hypochlorite ion. Okay, this much idea is there more than sufficient to work out questions in exam. Breakpoint chlorination test. Okay. Based on this, chlorine demand is equal to chlorine dose at breakpoint. Exactly at breakpoint, what amount of chlorine dose is required? This is chlorine dose at a breakpoint, right? What is combined chlorine residual? Combined chlorine residual is equal to residual available at breakpoint. Chlorine residual at breakpoint is called exactly at breakpoint. Whatever residual that is there, that is called exactly here, this much. That's called combined chlorine residual. Free chlorine residual is equal to combined chlorine residual minus combined chlorine residual minus, right, chlorine dose at breakpoint. Because curve is 45 degrees, exactly at 45 degrees, x is equal to y. So beyond breakpoint, x milligrams extra add, x appear as a free chlorine. Beyond chlorine dose at breakpoint, if you add, beyond breakpoint, if you add some y milligrams per liter extra chlorine that appear as a free chlorine only. Okay, this much idea is there. You can answer any question in disinfection also. Okay, if you have doubts, you can ask me. 5 minutes doubts. So between 4 topics, sedimentation and sedimentation ended with coagulation. One 2 marks question, guarantee. One question for 2 marks, guarantee 100%. Between filtration and disinfection, one question for 2 marks, 100%. So these 4 topics put together, you will get 2 solid 2 marks questions. For water quality, 2 questions you will get. So total marks you can get from these topics usually is 5 to 6, 6 to 7, 5 to 7 marks. It may vary anywhere. Okay, that's it. And remaining things in water supply beyond this is Hardy cross method basics. Hardy cross method, right? Those pipe equilibrium equations. Based on that, Hardy cross method is trial and error method. It is. Therefore, big questions, no way. Successive iterative method. So many iterations you need to carry out. That and all lengthy process. It's a 20 marks question. Therefore, rule out only basics you will ask. It is successive iterative method. So here we work out by pipe equilibrium equations are there. Based on that, any one question is possible. That is, at any pipe junction, flow in towards junction is equal to flow away from junction. Flow in towards junction is equal to flow away from junction. So Q values, missing Q values we can work out by using these equations. Sigma flow in at junction is equal to sigma flow out at same junction. Okay. Junction is 2 or more pipeline meeting point is called junction. Like road junctions, we also got pipe junctions. Then second equation is algebraic sum of head losses. Based on these equations, he is asking questions from Hardy cross method. Algebraic sum of head losses around a closed loop must be 0. Around a closed loop must be 0. Sigma H is equal to 0. These two conditions it are satisfied. Based on these two conditions, he is asking questions in GATE exam, Hardy cross method. This is water supply engineering. Now, if you have doubts, you can ask me. Yeah, anybody having doubts, you can ask me. Okay, doubts are not there, we'll go to wastewater engineering. First one, estimation of dry weather flow and wet weather flow. So how to dry weather flow estimated? Dry weather flow is equal to this population into per capita sewage flow. This will give dry weather flow. Sometimes dry weather flow estimated by using water supply also. So population into per capita water supply into factor. If water supply is given, then you have to multiply that water supply into factor, because we're talking about a drainage system. Sewage, what amount of wastewater coming out of this? Okay, that factor usually vary from 0.7 to 0.8. Fraction of water supply converted into sewage is nothing but fraction of water supply convert into wastewater and reach sewer. Okay, dry weather flow, that's how we work out. Then wet weather flow estimated by rational formula. Q wet weather flow is equal to, it is air by 360, where A is equal to catchment area in hectares. Substitute in hectares. I is equal to impermeability factor. Some people call it as runoff factor. This impermeability factor, runoff factor, sometimes people call it as K also, which is ratio between runoff by rainfall. Okay, so most of the urban catchments are so many surfaces having different imperviousness. In such case, average impermeability factor will work out. Suppose this is a catchment with the different surfaces. A1 area having I1, A2 area having I2, AN area having IN, like this. Then we will work out average I is equal to A1 I1 plus A2 I2 plus and so on to AN IN by 100. Right? Or AN IN by A. Sorry. A is equal to total area of catchment, A1 plus A2 dot AM. So that's how we can work out. Then R is equal to rainfall intensity in mm per hour. How to get this value? We measure rainfall intensity, rainfall depth we measure, rainfall depth by rainfall duration. R is equal to depth of rainfall. Rainfall is measured in terms of depth only. Duration of rainfall, how much rain has collected and how long it has collected. How long rain has occurred. R is equal to P by T. Okay. So sometimes this R, depth of rainfall, duration of rainfall is not there. Then by using one formula, R in mm per hour, straight away work out using a formula 25.4 A by Tc plus B, where Tc is equal to time of concentration in minutes. Time of concentration in minutes. So this time of concentration is equal to time of entry plus time of flow, where T is equal to time of entry in minutes. Q is equal to time of TE plus TF. time of flow in minutes. So most of the problems, T value is not there. So when T is not given, T is taken as equal to Tc. Then Tc is taken as equal to T. Then duration of storm T is equal to time of concentration. For which rational formula is applicable. So comfortably you can take it as Tc. Okay? This is how you need to keep the things in your mind related to dry weather flow and wet weather flow. Sewer design like open channel design only. So two equations we use. Design of sewer means cross section area. Cross section area of sewer you have to find out. And gradient of sewer. So to find out these two unknowns, what we do? We use two equations. Q is equal to area into velocity coupled with Manning's formula. V is equal to 1 by n, R by 2/3, S for half. Flow continuity equation. S is equal to slope of the sewer. So this S is equal to H by L also you can take. Truly speaking, slope of hydraulic gradient line, that is. Gradient means slope only. Okay. So two unknowns are there. R is equal to hydraulic mean radius, which is equal to wetted area by wetted perimeter. The ratio between wetted area by wetted perimeter. Wetted perimeter. So very popular question is, sewers always run partially full. Partial flow condition only we design. That means there is some empty space we always keep in a sewer to absorb fluctuations or variations in sewage production, because sewage is not continuously produced at constant rate. Sometimes more flow will get, sometimes less flow will get. Whatever may be the flow case, drains should not overflow and flood the roads and all, because they are laid below roads, so they should not flood the roads by overflowing these dirty things onto the roads. So therefore, to prevent that that overflow of floods, and as well as sewers always run with partial flow condition, we assume sewers are designed as open channels. So whatever concepts we use for open channel design, same concepts we can use for sewer design also. That's why Manning's formula coupled with the flow continuity equation are used to find the above two unknowns, cross section of sewer and gradient sewer. So Manning's formula coupled with the flow continuity equation. Manning's formula coupled with the flow continuity equation used to find two unknowns. Flow continuity equation are used to find the above unknowns. to find the above two unknowns. That's all. Sewer design. So for half flow condition, for full flow, sewer running full. Sewer running full, right? R is equal to A by P. Affected area is pi by 4 d square. Filter perimeter is pi d. So it is d by 4. Okay. For partial flow conditions, things will be different. So for full flow to partial flow, tables will be available. From there you can find out. So d by d ratio, q by q ratio, v by v, like that, a by a, r by r. Like this, we can draw all those things. The small q, small v, area, small a. Or sometimes we also read values from table diagrams also. Like these diagrams will be given. Here d by d is given, q by q, v by v, etc. So this small d represent the depth of flow. Capital D represent diameter of sewer. So based on d by d ratio, you'll get q by q and v by v. And capital Q, capital V, capital A represent for full flow condition. For full flow condition. Small q, small v, small a, etc. represent for partial full condition. Flow parameters for partial full condition. This is how we brought out relation between partial flow to full flow and work out the problems. Okay. So this is how sewer designs are made. Then after that, problems on BOD. Characteristics of wastewater. So BOD means always we measure 5-day BOD at 20 degrees Celsius. So 5-day BOD at 20 degrees Celsius we represent by Y5 at 20 degrees is equal to, it is DO initial minus DO final into dilution factor. So DO initial sometimes we are expected to work out. So VD into DOD plus VS into DOS by VD plus VS. VD means volume of distilled water used in dilution. distilled water with the DOD, dissolved oxygen with the DO. Vs is equal to volume of sewage sample with the DOS. Both of them we combine, prepare into a mixed solution. That mixed solution is called DO initial, where we prepare in a BOD bottle. So DO initial is equal to, which is nothing but DO mix. Two different solutions having two different values of DO, they are combined like this. This is a BOD bottle. This BOD bottle contains small amount of sewage sample, large amount of distilled water. This is sewage sample, VSML with the DOS. This is sewage sample. This is diluted with what? Distilled water. VDML of distilled water with dissolved oxygen, DOD. If you combine both of them, then you'll get that one. Two such bottles we prepare, one to find this is, and we find DO initial. One more bottle we prepare in the same way. This is incubated at 5 days at 20 degrees Celsius. Same way, sewage sample we provide. This is incubated after 5 days incubation. Same. This also contain VDML of distilled water, VSML of sewage sample. After 5-day incubation, at 20 degrees Celsius, final DO this is. DO final will find. Difference in DOs will give, right? This initial DO, that is final DO. Amount of oxygen consumed by microorganisms. Microorganisms, how much amount of oxygen consumed. So DO initial minus DO final is equal to DO used. DO initial minus DO final is equal to DO depleted. Depleted means DO used. Dissolved oxygen used. Okay. Then you can substitute in the formula and get the answer. This is the formula. DF stands for dilution factor, because when you conducting the test, so total sewage sample you can't take, so it dilution factor, which is nothing but 300 by Vs or 100 by percentage dilution, percentage sewage sample diluted. So 2%, 3% like that sewage sample is added. In that case, 100 by 3 by 100, 100 by 2 by 100 like that will take. Or otherwise you can convert that into 2% means 300 out of this capacity of this bottle is 300 ml. Capacity is 300 ml. 2% means 300 into 2 by 100, 6 ml. So 300 by 650 or 100 by 250. They both will give same. And we can also work out this BOD at any time, at any temperature. So BOD depends on time and temperature. This BOD curve, this is called ultimate BOD. To reach ultimate BOD, it takes time. So how it reaches ultimate BOD? Slowly it reaches there. So therefore, BOD at any time, at any temperature is equal to, it is YT. Right? Ultimate BOD, we take it as L0. So therefore, and BOD remained at any time is L0 minus YT. This is L0 minus YT. So this L0 minus YT is nothing but BOD remained at any time T and YT is equal to BOD removed. Oxygen demand met. So what we measure is amount of oxygen that is consumed by microorganisms is this much. Therefore, BOD removed at any time t removed from wastewater at any time t is equal to YT at any temperature, and because it depends on temperature also. This is curve for 20 degrees Celsius. Curve for 30 means still speed it reaches there. Less than 20, slowly it reaches there. So it is L naught into 1 minus e power minus k into t. Right? L naught is ultimate BOD. Ultimate BOD initial organic matter same. It's also equal to initial amount of organic matter in wastewater. So why we are measuring BOD? BOD is a measure of strength of wastewater. Therefore, 5-day BOD only we measure, standard that is. So BOD is a measure of strength of wastewater. We always measure 5-day BOD. Understood? So suppose somebody asked you 8 days BOD at 30 degrees. So how to find out 8-day BOD at 30 degrees? Y8 at 30 degrees is equal to, it is L naught into 1 minus e power minus k 30 into 8. That's all. 5-day BOD at 20 degrees means, so Y5 at 20 degrees is equal to L naught into 1 minus e power minus k20 into 5. The temperature and temperature k value changes. Time factor, time changes, time increase or decrease also taken into account. Or sometimes 3-day BOD at 15 degrees Celsius, somebody asked you, or at 10 degrees Celsius. Y3 at 10 degrees is equal to, is L naught into 1 minus e power minus k10 into 3 days. Like this will work out. So L naught always remain constant. L naught doesn't change with time and temperature. Does not change with time and temperature. Always remain constant. So in general, BOD at any time at any temperature is equal to BOD at any time t and at any temperature t degrees Celsius is equal to is L naught into 1 minus e power minus k t into t. So this k is known as BOD rate constant, whose value depends on temperature. Kt is equal to BOD rate constant at a temperature T. So K at any temperature is equal to K20 into 1.047 T minus 20. So using this equation, you can work out K20 value, Kt value, K at any temperature. So K20 value to find, K20 value will be given to you. So this K20 value to the base E given to you, or sometimes K20 value given to base 10, that you convert into base E. Base 10 into 2.3. You multiply, then you'll get K20 value to the base E. Otherwise, you have to change your equation. Instead of taking e power minus kt, you have to take 10 power minus kt. So instead of changing logarithm, so I change 10 base log to natural log by multiplying k value given to base 10 to k base E by multiplying with 2.3. So that's how we can work out. Okay. So any problem you can find and work out with the help of this equation. I'll have one more break. I'm getting sleep. Okay. One more break. So then I'll complete this. Just 10 minutes break. Okay. Yeah, next is if primary treatment, anything that they ask in the exam is, of course, one more question is there in this. One more important topic in BOD topic is population equivalent. So population equivalent, we can work out by using equation total BOD by per capita BOD. Total BOD we work out in kilograms per day by multiplying Q with Y, Y5 20 degrees by per capita BOD. Per capita BOD is constant. This is Q substitute in MLD, this is in milligram per liter. This product will give answer in kilogram per day by kilogram per person per day. Therefore, you will get answer in persons. So this per capita BOD usually varies from anywhere between, this will be given to you constant as per Indian condition, it is 70 to 90 grams per day. 90 grams per person per day, like that, grams per person per day. That's how we need to read. Okay, that is one more important topic in BOD. In addition to that, what else is important is in primary treatment, grit chamber is important. Primary treatment, right? It is screen, grit chamber, skimming tank, and primary clarifier. Among all these, grit chamber is important. So grit chamber is very, very important. This is, if at all any question they ask, it's only grit chamber. So grit chamber design also same as design of sedimentation tank. Right? It is based on detention time. We provide 1 to 3 minutes in grit chamber. Using detention time, we can find out volume of grit chamber. Grit chamber is rectangular tank. Its volume is equal to Q into detention time. This volume is equal to L into B into H. And one more important parameter is flow velocity. Usually we provide flow velocity 0.3 meters per second. Right? Using this, you can find out cross-section area of grit chamber. Cross-section area of grit chamber. So it is equal to Q by VH. Cross-section area means B into H. It's equal to Q by VH you will get. Okay. Then rest of the things we can work out with the help of that one. Similarly, we can also use surface loading rate, surface overflow rate also. Surface area also you can find out. Surface area of grit chamber is equal to Q by V naught. V naught is equal to surface loading rate or surface overflow rate. Then for 100% removal of grit, you can also use that formula. For 100% removal of grit particles, right? You can use sedimentation tank formula. H by VH should be less than or equal to L by VH. And length of grit chamber you can find out. Length of grit chamber L is equal to, it is VH into detention time. This will give length of grit chamber. And settling velocity of grit particle, Vs is equal to settling velocity of grit particle. You can work out G into S minus 1 d square by 18 mu for laminar flow condition. Or any other flow condition prevail, you can apply Stokes equation and work it out. Okay. So that's all. Remaining things are light, not required. Then the next topic is activated sludge process. In activated sludge process, all design parameters are important. Activated sludge process, design parameters they will ask. One is F by M ratio. F by M is equal to Q into Yi minus, use this formula, okay? Yi minus Ye by V into X. So usually Y, since Y is negligible, so some people neglect. Therefore, Y, some people take it as 0. Then in that case, F by M also equal to Q into Yi by V into X. But better is always take this one, okay? If not given, we can take 0. If Y is not given, you can take it as 0. Then second formula is Mean cell residence time. It is denoted by theta C. Food to microorganism ratio by means. So it is V into X by QW into XU plus only formula I have to remember Q minus QW into XE. If you know formula, you can write all those things. You can work it out. Mean cell residence time. This QW into XU plus Q minus QW into XE is known as solids wasted. Solids wasted per day. Okay. If XE is not given, then XE also can be taken as 0. Then XE is taken as 0. If given, well and good. So only two parameters you can take 0. One is YE, other one is XE. If given, we'll take YE and XE given, we'll take. Otherwise, we'll take them as 0 if required. If required, we can take them as 0. Okay. Third, volumetric loading rate or BOD loading rate or organic loading rate. Volumetric loading rate. This is also known as BOD loading rate. It is Q into YI by V. This we substitute in MLD, this in milligram per liter, this in meter cube. Therefore, we'll get volumetric loading rate in kilograms per meter cube per day. So F by M unit is day inverse will get. This theta C will get so and so days. Okay. F by M day inverse. Substitute Q in meter cube per day, YI in milligram per liter, V in meter cube, X in milligram per liter. They cancel out, we'll get this is in 1 by day, so that we can write it as day inverse. Theta C will get straight away in days. Okay. Volumetric loading rate. Then efficiency of BOD removal is equal to this BOD removal efficiency. BOD removal efficiency is equal to is YI minus YE by YI into 100. Okay. The fifth one, aeration period. Aeration period. How long wastewater is aerated? Nothing but detention time only. This is equal to V by Q, where V is equal to volume of aeration tank. Aeration tank is rectangular, therefore it is L into B into H. Next, what else is expected is sludge volume index. It is called SVI. Sludge volume index is equal to space occupied by sludge. Space occupied by X. X means grams. Space occupied in ml by X value substituted in grams. X is equal to MLSS. X is MLSS concentration. Mixed liquor suspended solids concentration. Sludge volume index. Seventh one is recycling ratio. QR by Q is equal to, it is X by XU minus X. Sometimes we'll ask QR also. So from this you can write QR is equal to is X by XU minus X into Q. Like that also you can find out QR value. Recycling rate. Rate of return sludge this is. You can find out with the help of this one. Okay. You are familiar with all these formulae. Comfortably you can work out questions related to activated sludge process. Okay. More than sufficient. This is trickling filters. To trickling filters, only efficiency formula, BOD removal efficiency of trickling filter is equal to trickling filter is equal to, it is YI minus YE by YI into 100. YI is influent BOD. Actually, you can work out like that, but we use NRC equation. This is also equated to NRC equation. This is called NRC equation. 100 by 1 plus 0.0044 into root of Q into yi by V into F. This equation is called NRC equation. NRC of United States of America equation. This is empirical formula. National Research Council of United States of America equation this is. Okay. In this equation, Q into yi by V is called BOD loading. BOD loading rate or organic loading rate. Or organic loading rate or volumetric loading rate. This is expressed in kilogram per hectometer per day. The empirical formula, no? So equations are important. This Q into yi in this equation is called BOD applied to trickling filter. Total BOD applied to trickling filter. Right? V is equal to volume of trickling filter. This is in kilogram per day. This is in hectometer. So once you get volume, so depth of trickling filter we assume. Depth of trickling filter, it may provide 0.9 meters to 2.5 meters. Then we find out area of trickling, surface area of trickling filter. The circular tank, therefore pi by 4 d square, which is equal to is volume by depth. Depth h this is. So therefore d you can find out. So this is called diameter of trickling filter. D means diameter of trickling filter, you can find out. That's what is called design. So in this equation, yi is influent BOD. Of course, 5 BOD only. And y is effluent BOD. You can also equate this to normal equation, BOD equation. Efficiency also equal to yi minus ye by yi into 100, which is also equated to NRC equation. Like this, you can equate and work out whatever. Depending upon your efficiency, size of the trickling filter depends. Then that F value in that equation is called recirculation factor. This F value we calculate by using equation 1 plus R by I by 1 plus 0.1 R by I whole square. This R by I is known as recirculation ratio. R by I is known as recirculation ratio. So R by I is known as effluent recycled to influent applied. So sometimes instead of disposing effluent, we can recycle also. So influent applied to trickling filter. So based on F, there are two types of trickling filters are classified into two categories. Classified into standard rate trickling filters and high rate trickling filters. Call them as SRTF. For standard rate trickling filter, R is equal to 0, then R by I is equal to 0, then F is equal to 1. Then high rate trickling filters, we call them as HRTF. R is greater than 0, R by I also greater than 0, then F is greater than 1. So remember these values. Substitute here in this equation, we'll get that F value. That's all. That is the difference between standard rate and high rate. There is no recirculation in case of standard rate. There is a recirculation recirculation of treated effluent in case of high rate trickling filter. So because of recirculation, what happens is influent BOD, some 200 is there. Because of recirculation of less strength waste, that is decreases to less than 200. So in case of standard rate, there is no recirculation, 200 we apply. Therefore, it requires huge space. Standard rate require high space, high rate require low space. That's the difference. That's all. That much idea is there, more than sufficient. For GATE exam point of view, revising the content, not for IES. Next, coming to sludge treatment. So we need to remember two equations: volume reduction of the sludge. How sludge volume reduces in sludge treatment. So Vt is equal to, by reducing moisture content, sludge volume decreases. V2 into V1, where P1 is equal to percentage moisture content of the sludge. Before treatment. Vt is equal to percentage moisture content of the sludge. After treatment. Vt is equal to volume of sludge after treatment. V1 is equal to volume of sludge before treatment. Based on this equation only, any question is possible in the exam. Beyond that, no way. Then to carry out this sludge treatment, we require one unit called sludge digester. Sludge treatment is carried out at sludge digester. Sludge treatment is given at a sludge digester. So sludge digester is a circular cylindrical tank. It is a anaerobic circular cylindrical tank. Anaerobic means completely cut off from the air. Circular cylindrical tank. So any question is possible, that is capacity of digester. Capacity of sludge digester. That is nothing but volume. So it is V1 plus V2 by 2 into T. This T is known as digestion period. This V1 is equal to volume of fresh sludge. Fresh sludge has got moisture content P1. So 100 by 100 minus P1 into M1 by rho sludge 1. And V2 is equal to 100 by 100 minus P2 into M2 by rho sludge 2. So volume of sludge. So M1 is equal to, it is Q into concentration of solids in sludge before treatment. M2 is equal to Q into concentration of solids in sludge after treatment. So sludge solids content also decreases. We destroy some of the volatile solids present in that. So M1, M2 can calculate. Rho sludge 1 is density of sludge before treatment. Rho sludge 1 is density of sludge before treatment. Rho sludge 2 is equal to density of sludge after treatment. So using these values, you can find out V1, V2 and substitute in the formula. Here not required straight away. V2, V1 you can calculate by using this equation, knowing the moisture contents. Right? That much accuracy is not required. For 1 mark, 2 marks, this you can use. Sometimes taking that solids variation also you take, then we work out V1, V2 using this. Here, if M1 is equal to M2, rho sludge 1 is equal to rho sludge 2, then V1 is equal to V2, V1 relation we can brought out. Here we assume that in this equation, M1 is equal to M2, right? Here M1 is equal to M2 assumption. Based on assumption, we derived this. And rho sludge 1 is equal to rho sludge 2. Actually, V1, V2, you have to work out like this. But that much accurately, 1 mark, 2 marks not required. M1, M2 we assume same. No change in solids content. No much change in density of sludge. Then this equation reduces to simple form. This is how we work out the things, okay? Based on assumption, this we work out. That don't confuse here, okay? For 1 mark, 2 marks, assumption. For no change in solids content, for no change in much change in moisture content, then you can use this equation and work out. That's all. Digestion period usually vary from temperature. Digestion period depends on digestion time or period, whatever it may be. Depends on temperature. At the temperature T. At T is equal to right, normal room temperature. If you carry out, it may room temperature means 10 degrees to 40 degrees Celsius. If you carry out, right, this T value you can take 30 to 60 days time it will take. At a temperature 45 degrees Celsius to 60 degrees Celsius you carry out, and T value can decrease to 15 to 25 days also, right? So this is called mesophilic range of digestion. This is thermophilic range of digestion. This and all there in notebooks and all. You go through that notebooks, you will get idea. That's all. That's about sludge treatment. Next is septic tank design, also same as the sludge tank. Septic tank design, sometimes they may ask you. So septic tank design means capacity of septic tank. Capacity of septic tank is nothing but volume of septic tank. Septic tank also anaerobic reactor only. V is equal to, it is volume of settling zone plus volume of sludge zone. So V is volume of settling zone of septic tank. V sludge is equal to volume of sludge zone of septic tank. Okay. So volume of settling zone we calculate by using detention time, Q into detention time. Detention time usually we provide 24 hours to 48 hours. Right? Q is nothing but number of users into per capita sewage flow. From that you will get the Q value. So volume of settling zone you get. Volume of sludge zone, to get volume of sludge zone is equal to, it is rate of sludge production into number of users into, okay, cleaning period or desludging period. Multiply, then you'll get that one. RSP means rate of sludge production. This will be given to you. Normally, this is anywhere in for Indian condition, rate of sludge production is, it may vary anywhere between for Indian condition, rate of sludge production vary anywhere between 30 to 40 liters per person per year, right? And similarly, cleaning period is usually taken, cleaning period, but some people call it as desludging period. Sludge removed from the septic tank or sludge is cleaned from the septic tank is 1 to 3 years. Number of users that is known to you, then multiply, then you will get volume of sludge zone you will get. So if you add both of them, you will get total volume of septic tank. So volume of settling zone plus volume of sludge zone will give total volume. Then area of septic tank is equal to surface area. Area means plan area will get. Surface area of septic tank is L into B is equal to it is volume by depth. H is equal to depth of septic tank. Septic tank is equal to, it is small h plus H sludge. Small h is known as liquid depth. H sludge is known as depth of sludge zone. Or small h also you can take. Small h sludge, depth of sludge zone. So you'll get total depth. Or otherwise, volume of settling zone by liquid depth also you can take. That way also you can find out surface area. Then L is to B ratio will be given. Then you can find out length of the tank and width of the tank. That's how we design the septic tank. Septic tank design also important sometimes for exam because they are very popular in India. Then oxidation ponds. Oxidation ponds also very popular in India, but we design them. Surface area of oxidation pond required is equal to, surface area means plan area. Surface area of oxidation pond required is equal to, it is total BOD applied by BOD loading rate. Total BOD applied to pond by BOD loading rate or organic loading rate. So surface area of pond is nothing but L into B. Total BOD applied to pond is Q into YI. BOD loading rate is organic loading rate. OLR means organic loading rate, which is nothing but BOD loading rate. So this you substitute in MLD, this in milligram per liter, kilogram per day. This is kilograms per hectare per day. They cancel out, you'll get the answer in hectares. So L into B, you'll get so and so hectares. Then using L is to B ratio, you can find out length of the tank and width of the tank. You can convert this into meter square by multiplying with 10 power 4. Then you can find out length of the tank and width of the tank. This you can find out. Okay, that's how we can fix up. Then second design parameter, detention time. So volume of oxidation pond is equal to Q into detention time. This will give volume. This volume is equal to L into B into H. So detention time approximately you can find out by using equation 1 by K into Ln Yi by Ye. Yi is influent BOD, Y is effluent BOD. That is understood, no? K is BOD rate constant, nothing but pond rate constant, which has got units of 1 by day inverse. So therefore answer will get so and so days straight away. Milligram cancel out, 1 by day, this days will go to top. Okay, this is nothing but BOD rate constant only. There is another way of working out dimensions, or otherwise simply we can work out, you can ask detention time, or you can ask length of the tank, width of the tank, something like that. 1 mark, 2 marks, you can't expect anything beyond this. Okay. I'm not feeling well, but yet because they're asking me to complete. Okay, then oxidation ponds is one, a septic tank. Both of them are important. After that, one more important topic is disposal. In disposal of effluents, only one question they'll ask, that is mixed formula. Based on mixed formula, so there is a river flowing here. You are disposing wastewater into this. Somewhere here, we dispose wastewater, dangerous waste. Wastewater effluent is disposed here. Effluent means treated wastewater. How much amount is disposed? Q amount of wastewater with a concentration of pollutant CW disposed into river here, somewhere here. This upstream side of the river and this is downstream side of the river. river flowing from upstream to downstream, like this. So before disposal, the flow rate in river is QR. Concentration of that pollutant is CR, almost close to zero. If somebody else dispose there, or otherwise little concentration will find there, very small amount. Okay. Then immediately after mixing here, concentration of pollutant in the river on the downstream side is C mix. As you travel more and more on downstream side, C mix become zero also after some time. So the C mix is equal to, it is Q river into C river mix formula. Different solutions with the different concentration if you mix, you will get the concentration of that mix using this formula. And it slowly becomes zero. C at any time, concentration of this pollutant at any time T. Suppose you travel L meter distance in the river on the downstream side. To travel L meter distance, it takes T amount time. Then concentration of pollutants on the downstream side at L meter distance on the downstream is equal to, sometimes they'll ask, this time. So concentration of pollutant on downstream side. Concentration of pollutant on downstream side. Pollutant on downstream after disposal. After disposal of effluent. C T is equal to, it is C mix, it exponentially decreases minus K into T. So K is rate constant. At what rate that disappear? Its unit is 1 by day. We write it as day inverse. T is equal to time in days. You substitute, then we'll get, because it decomposes as it travel more and more, concentration decreases. Therefore, so concentration of pollutant in the river after disposal of effluents on the downstream side is equal to, on the downstream side is equal to, it is CT, which is nothing but C mix into e power minus KT. How to find out this T time? T is equal to time taken to reach there. Time taken to travel L distance and downstream. How to find out this? So distance traveled by velocity of flow. Velocity of flow in the river. Velocity of river flow. So that will give L value. So L by V you take, you will get T value. That substitute here, you will get concentration of pollutants downstream side, 1 kilometer, 2 kilometers, 3 kilometers. As you travel more and more, concentration decreases. That's all. Beyond this, you can't expect anything from the effluent disposal. Okay. Then one more topic is solid waste management. Here only one common sense type of questions they'll ask. Solid waste management also big topic, but only one question possible is landfill design. Yeah. What is Srikanth? What is your doubt? Yes, Srikanth, you can ask me. Unmute and ask Srikanth. Okay. Solid waste disposal by landfills is very, very important. So except that you can't expect anything from here. Solid waste management means it is generation, collection, transfer and transport. All of them put together is called solid waste management. Disposal. Say processing and recovery and disposal. A big topic it is, but all of them are not required. This whole thing put together, it is solid waste management. Generation usually, normally for Indian condition, rate of generation is, as per IS code, it is 0.4 to 0.8 kilogram per person per day. Using this, what you can find out total solid waste generated per day. So therefore, total solid waste generated per day is equal to solid waste generated per day by a city is equal to, it is rate of generation into population. Rate of generation into per day this much, per month how much, per year how much, like that also you can find out, into population. Or total solid waste generated in a given time is equal to total solid waste generated is equal to, it is rate of generation into population into time in days. How many days? Per month or per day or per year, something like that. For yearly you want 365, right? Per month means 30. Per day this is per day into time in days you multiply, then you will get total solid waste generated in a given time, T. Okay? That's how we can work out total solid waste generated. Then collection by bin system. Collection is made by bin system. So what is the size of the dustbin, size of bin, number of bins, this and all expected to calculate. Number of bins required, time to fill bin, this and all we work out here. Transfer and transport by trucks. Transport by trucks. It's called hauling system. Employing trucks. Here we'll find out number of trucks required, size of each truck, number of trips per day, time for each trip, cost for each trip. Like this, so many number of things we work out here. But that much depth so far not asked, but this is the thing. But just by looking at the data given there, you can work out. Then processing and recovery, what we do is we segregate the waste. What we carry out is segregation of waste is carried out. And we segregate into different categories. One is disposable waste, recyclable waste, reusable waste. So disposable waste go for disposal, reusable go for reuse. Disposal by landfilling, incineration means burning, or composting. So many methods also there but not required. Pulverization, seed disposal, like that. So many are there, but among them one possible question is landfill. Design of landfill. Landfill is an earthen pit. So what is the size of the landfill required? Size means area of landfill required, otherwise area or volume of landfill required. It's called design. So to find this, what we do is first we work out total solid waste generated per day or per in a given time for which fill is to be accommodated. Total solid waste generated in given time t. It is rate of generation into population into t in days. Then we'll get so and so kilogram. This is. After that, we'll find out volume of compacted solid waste in the field. is equal to total weight of solid waste generated. This is total weight. I'll put weight here. Total weight of solid waste generated in given time is equal to this. Volume of compacted solid waste in the fill is equal to total weight of solid waste generated by density of compacted solid waste. Density of compacted solid waste is given to you. Okay, so once you get that, depth of fill will be given to you. Depth of fill be h. Then area of so volume of compacted fill is equal to, if fill is packed to the top, volume of compacted fill is equal to, because after dumping the solid waste we compact also. So volume of compacted solid waste in the fill. Then depth of compacted fill is equal to h. Let us assume. Then area of compacted fill is equal to surface area, that is L into H, L into B, which is equal to volume by depth. So that's how we can work out area of fill. Finding area only, how many hectares of land required for 1 year, for 10 years, for 5 years, like that question they'll ask. Or volume they may ask. So that's what they are expected. Remaining things are common sense type of questions. They'll ask what is the specific gravity of solid waste. 100 by specific gravity of municipal solid waste is equal to percentage of component 1 in solid waste by specific gravity of component 1. Solid waste is a heterogeneous mix of so many number of things. So like this based on this also one question is possible. MSW means municipal solid waste. Municipal solid waste is heterogeneous mixture of so many number of things. You'll find paper, percentage paper by specific gravity of paper, percentage plastic by specific gravity of plastic. Like that, it is heterogeneous mixture of so many number of things. Any kind of heterogeneous mixture, specific gravities are worked out by using same formula. Okay, that is the one. Then energy content, sometimes they'll ask. Energy content of solid waste is equal to total energy content as discarded. Without making anything you want to work out, it is sigma percentage of ith component into energy content of ith component into 100. Vi is equal to percentage of ith component of solid waste, ith component of MSW. Ei is equal to energy content of ith component. So each component has got certain energy content. Ith component of MSW. Okay. Sometimes energy on dry basis. If you dry the solid waste, then energy content still increases. Energy on dry base is equal to, it is energy as discarded, total energy as discarded into 100 by 100 minus percentage moisture content of solid waste. Energy on ash free dry basis. Ash also if you remove, still energy content still increases. This is total energy only. This is total energy as discarded. Okay. And ash free dry base is equal to total energy as discarded, or simply energy as discarded into 100 by 100 minus percentage moisture content minus percentage ash content. So like this, energy keep on increases. That is one possible question. Okay. Or here instead of Specific gravities, mass density is also there. 100 by density of MSW is equal to percentage of component 1 by density of component 1. Like this also you can work out straight away. Okay. So generally graduate aptitude kind of questions they will ask in solid waste. The last topic is air pollution. Noise pollution is not there for you from this year onwards. Extra topics are not at all required. You can ignore them. Just go through once and ignore. You have covered, just go through once and afterwards you can ignore. Air pollution. Air pollution also important topic. రావడం లేదమ్మా చూడు మళ్ళీ బంద్ అయింది. సెన్సిటివ్ ఉంది బాగా అది.
వైర్ అంటే ప్యాకింగ్ ఈ మధ్య బాగా అయినాయి వైర్లు కొంచెం యూజ్ అయింది.
In air pollution, what is important is the main pollutants, primary pollutants and secondary pollutants. Primary air pollutants. There are so many number of primary air pollutants. Among them, very important are particulates. Particulates we call them as SPM, suspended particulate matter, or TSP, total suspended particulates. Nothing but suspended particles. Carbon monoxide and their derivatives, SOx, oxides of sulfur and oxides of nitrogen. These are important. Secondary air pollutants. Primary air pollutants react with each other and produce secondary air pollutants. Most of them are formed by photochemical reaction. Ozone, PAN, peroxyacetyl nitrate, peroxybutyl nitrate, peroxypropanol nitrate. Start with P is a secondary pollutant. Smog, smoke plus fog, like this. They're all secondary pollutants. Secondary pollutants, they form in atmosphere. Primary air pollutants, they release from the ground, remain as it is. No change happens. Primary pollutants, when they change into different kind of pollutant, they are called secondary pollutants. Yeah, Mohammad Shaj raised hand. What is Mohammad Shaj? What is your doubt? Doubts are not there, don't raise hand. Okay. So that is the one thing, primary pollutants. And concentrations of these pollutants expressed. Concentration of air pollutants expressed in terms of ppm or ppb or microgram per meter cube. These conversions they are asking because since 1 ppm is not equal to 1 milligram per liter for gases. This is true for gases. 1 ppm is equal to 1 milligram per liter for liquids. Water and wastewater, 1 ppm is equal to 1 milligram. For gases, no. Therefore, this conversion is very popular question. Therefore, how to convert ppm to microgram per meter cube and microgram per meter cube to ppm? How to convert? So we carry out conversion. 1 ppm of any air pollutant is equal to 1 into m by k into 10 cube microgram per meter cube of that air pollutant. Okay, 1 microgram per meter cube of any air pollutant is equal to 1 into k by m into 10 cube ppm. What is this m? What is this m? That idea is there how to calculate m and m, then you can work out this conversion from ppm to microgram per meter cube. So this m is equal to molecular weight of any gas, gaseous pollutant only, no? SOx means SOx, NOx means NOx. Molecular weight of, because gases only changes concentration. M is equal to molecular weight of air pollutant. Gases contaminant, no? Carbon monoxide, this and all. SOx means carbon dioxide means carbon dioxide. Right? K is equal to constant. This K is equal to, it is RT by P into 10 cube. Or otherwise, RT value sometimes not given, R value not given, 10 power minus 3 into T by P. Okay? So in this equation, R is known as universal gas constant. Universal gas constant, whose value is equal to 82.05 into 10 power minus 6 atmosphere meter cube by mole Kelvin. That value substitute and simplify, we'll get this one. T is equal to temperature in degree Kelvin. Temperature in degree Kelvin, and P is equal to pressure in atmosphere. That's all. Pressure in atmosphere. ATM means atmospheric. Pressure expressed in atmosphere. 1 atmosphere is equal to 760 mm of mercury. That is 0.76 meters of mercury. Approximately 101.4 kilonewton per meter square. That is the meaning. Or kilopascals. Understood? How to convert kilonewton per meter square to atmosphere to that conversion is also important. Sometimes it is given in kilonewton per meter square, convert into atmospheres. Okay? Degree Kelvin, degree centigrade to degree Kelvin, how to calculate? So degree Celsius, temperature in degree Celsius plus 273. Then you get temperature in degree Kelvin. Okay? That conversion. Similarly, ppb it is given. So ppb to microgram per meter cube to ppb. So 1 ppb is equal to 1 into it is m by k ppb. Sorry, microgram per meter cube. If you remove the 10 cube, this become ppb. 1 microgram per meter cube is equal to 1 into k by m ppb. So k and m calculated in the same fashion. So that's one part, very, very important. Conversion is very, very popular question in GATE exam. IS they don't ask because calculator, without calculator you can't work out. In addition to that, effects of air pollution, that and all theory, you can go through that, what kind of problems are there on human beings and animals and plants, and what kind of problems it causes to property and all. That and all go through notes. Okay. Then meteorology, lab state is important. Environmental lab state. Environmental lab state keep on changes, which is nothing but dt by dz. So it is T2 minus T1 by Z2 minus Z1. Atmospheric lab state it is. Atmospheric lab state is called environmental lab state. Another one is known as adiabatic lab state. Adiabatic lab state is minus 1 degree Celsius per every 100 meters. Correct value is minus 9.8 degrees Celsius for every 1 kilometer rise, but it's a minus 0.98 degrees Celsius per 100 meters. So it is approximated as, easy to remember, minus 1 degree Celsius per 100 meters. It's called adiabatic lab state. ELR is called environmental lab state or atmospheric lab state. Hello? Yeah, who is it? Environmental lab state this is, which keep on changes from time to time and place to place, which change from time to time and place to place. ALR is adiabatic lab state, which is always constant, whose value is minus 1 degree Celsius per every 100 meters, which is always constant, and whose value is equal to minus 1 degree Celsius per 100 meters. So temperature decreases with altitude. So lab state is nothing but change in temperature with the altitude is known as lab state. Lab state means dt by dz. That is change in temperature, either decrease or increase, no matter. Usually temperature decreases with altitude, with the increase in altitude. Altitude means height. It's called lab state. Okay. Based on that, they will ask questions. Lab state questions they will ask. Based on this lab state, this is a temperature profile. This is a Z. This is temperature. So ELR is always constant. This ELR, ALR is always constant. If ELR lie below ALR, this represent unstable atmosphere, good for pollutant dispersion, unstable atmosphere, right? Good for pollutant dispersion and dilution. Therefore, concentration of pollutants will be very less. Pollutant dispersion and dilution. Therefore, any amount of pollution you release, no problem happens when ELR is greater than, this is ELR greater than ALR, right? Then second is ELR less than ALR. ALR is always constant. If ELR line lie above ALR line, this is ELR line. So this is ELR less than ALR. This represent stable atmosphere. It is bad for pollutant dispersion and dilution. So therefore, there is no much dispersion dilution occur. Concentrations will be high. The third one is inversion, exactly opposite. This is a ALR line. If ELR line go this way, instead of decreasing temperature, temperature increases. This is called inversion. ELR is negative lab state. When ELR is negative lab state means increasing temperature with a negative lab state. It's called inversion. It is worse. Worse means very bad for pollutant dispersion and dilution. So he will ask you whether concentration is more, concentration is less. So concentration is less when good dilution occur. Concentration is more when no dilution occur, poor dilution occur. When inversion, do no dilution dispersion, therefore concentrations are very, very high. Pollutant concentration in atmosphere is very, very high. So usually this ELR ALR line changes like this. So ELR line always remain constant, it doesn't change. This is always ALR. But ELR line keep on changes. Sometimes here, sometimes there, sometimes here. 360 degrees it changes. ELR line. So sometimes it is here, sometimes it is here, sometimes it is here. I'll take one more reference point here, this isothermic condition. So it keep on changes 360 degrees like this. So if it lie here, atmosphere is unstable, good for dispersion and dilution. If it lie somewhere here, atmosphere is stable, it is poor atmosphere. If it lie ELR line anywhere here, atmosphere is very poor. Unstable, stable, and very stable. Very stable atmosphere, very poor condition. Very bad it is. It is bad atmosphere, it is just bad atmosphere, it is good atmosphere. That's what. Good for what? Dispersion and dilution. So this is what, this idea should be there related to that, more than sufficient. Then air pollution control devices. I can't teach you everything in 1 hour, 2 hours. Just I'm giving brief idea. Air pollution control devices. And there sometimes they will ask some numericals also. One is particulates are controlled by some kind of devices and gas are controlled by some kind of devices. Particulate control devices are, one is gravity cycling chamber, then cyclone, gravity settling chamber, then cyclone separator. All is a separate particulate matter. Separate particulates from gases. Particulate matter from gases. Cyclone separator it is called. Electrostatic precipitator, popularly used at thermal power stations to control fly ash. Very costly they are. And these two are remove fine particles, fabric filters. Coarse particles taken care by, very coarse particles are taken care by fabric filter. So this remove diameter of the particle greater than 50 micron and efficiency of particle capture is less than 50%. This remove diameter of the particle 5 to 25 micron and efficiency of particle capture is 50% to 90%. And the electrostatic precipitator remove particulate of diameter greater than 1 microns, efficiency is 95 to 95%, 99%. Fabric filters remove diameter less than 1 micron and efficiency is greater than 99%. So very fine particles taken care by these very fine particulates. Particles. This is coarse particles. Slightly coarse particles are controlled by these devices. That much idea is there, more than sufficient. Similarly, gaseous control technologies. Gases, how dirty gases are controlled. There are three ways. One is absorption, combustion. Among them, the best is combustion. One is absorption, and combustion. Combustion means burning at high temperature, at elevated temperatures. That's it. This much idea is there, more than sufficient. Yeah. Overall idea I gave. So in detail, you prepare notes on your own important formula and all. Just go through them once. So last minute preparation, 2-3 days, you can revise all of the formulae thoroughly. Then sample questions, if you solve from previous GATE exam papers, if you solve, more than sufficient for EE. EE is the one where you can score maximum. Maximum marks you can score from EE. Believe me, trust me, just go through notes, sufficient. Whatever we discussed in the class, that is more than sufficient. So whatever questions we have solved in the class, just go through once. Almost all of them are old GATE questions. They're all model of questions, right? So from them only they change data and give, because they can't create new things every year. Once in 10 years or once in 5 years, one strange question you'll find. For that, you need not put any extra effort. If it is difficult to you, it is difficult to everybody. Keep that in your mind. Prepare well. God bless you. All the best. Okay. So if you have doubts, you can ask me quickly. I'll be available 5 more minutes. You can ask me. Like any other class, no doubts for you. Okay, anyway, I'll sign off. Yeah, Vishnu Prasad, 1 minute. Wait. I've given a nutshell. In detail, I have not discussed, because 3 hours, 2 hours, I can't discuss in detail. సేవ్ చేసిన, సేవ్ యాజ్ కూడా కొట్టినా, మళ్ళీ ఫైల్ నేమ్ పెడతాడు నేను. పెట్టావా? అవసరం లేదా? ఓకే, ఒక పిల్లగాడు డౌట్ అడుగుతున్నాడు. Vishnu Prasad, yes, you can ask me. What is your doubt?
Hello, sir.
You can ask. Yeah.
Sir, one previous question doubt, sir.
Yeah.
Can I read the question, sir?
Yeah.
Okay. The wastewater having an organic concentration of 54 mg per liter, following steady rate as 0.8 meter cube per day, and they give the dimensions, sir. I mean, detention.
I know that question. Okay.
Sir,
You flow balance, you take mass balance, you take, you will get it. Everything
two
we
kind
derive
of
from mass balance only because they are there in equation form. That's why you don't remember. Because in the class, I don't derive all those things. Everything based
no,
on
sir.
that
They
any
give two kind of solutions, sir. Like
because listen. Two kinds of that is one is given wrong solution. Don't follow that. Okay.
okay. Sir.
Two
Okay, sir.
solutions
Okay,
are
sir.
there. Only one solution is correct. Because so many teachers teach here with some I can't comment them.
Okay, sir.
So this is a reactor. Okay, mass neither be created nor destroyed. Suppose you apply a flow with concentration C in, so it flow from one end to other end. Any kind of operation like this only. So concentration changes, no, because some
Yes,
reactions
sir.
happen. So volume of this container is V, right? Volume of this container is
Sir.
V. It take T time to travel from one end to other end. So apply mass balance. So changes happens at a rate K in there, K, rate of reaction, that is. Okay. So mass balance is equal to mass flow in is equal to mass flow out. Mass
Okay,
flow
sir.
rate in
Okay.
is equal to mass flow rate out. Okay. What is in? Mass flow rate in. Q into C in is equal to mass flow rate out. Q into C out plus K C
V.
C out. This is K C out into V. So if you use this equation and you can work out whatever you require. Sometimes C in may be unknown, C out may be unknown, sometimes volume may be unknown, sometimes rate of reaction may be unknown. So something like that
Okay,
they will
okay,
ask
okay.
you. Okay.
Okay, sir. Okay, sir. Got it.
Mass neither be created nor destroyed. We all know that.
Okay, sir.
It
Okay.
only changes from one form to other form. Some escape, some
Okay.
remain in the tank. So remain in the tank is this, escape is this. Remain in the tank
Okay.
is K C out V, escape is K C out. In is equal to C in. Mass in is equal to K into C in, mass out is equal to, so going out of the process, K C out escape, V into K, after change it remain at the bottom. Okay.
Okay, sir. Okay.
Understood?
Understood.
Units also, see the units. Suppose you substitute this in meter cube per day, C in milligram per liter. Suppose for example, this also meter cube per day, milligram per liter. K unit is obviously 1 by day, day inverse. C out is milligram per liter. V unit is meter cube. Now everywhere unit is what? It is meter cube per day, milligram per liter. Meter cube per day, milligram per liter. Also meter cube per day, milligram per liter. Balance, no?
Yes, sir. Sir.
You can simplify.
Okay, sir. Okay, sir. Thank you.